Welcome back. In this video, we continue our discussion of multivariable limits by talking about the informal or imprecise definition of multivariable limits, interpreting this definition, and then using this imprecise definition as a justification for some theorems. A limit of a two-variable function is similar to a limit of a one-variable function in the sense that we study the output values as the inputs get closer to a constant. For a function f of x, comma y with two variables, we say this function has a limit L as the input points P with coordinates x, comma y approaches a fixed point in the domain P naught with coordinates a, comma b, if the distance between f of x, y, and L, which is measured as an absolute value, this is not a two-norm, the output of f of x, comma y is a real number, L is a real number, so the distance between them we measure as the absolute value. We say that the limit of f of x, comma y as xy approaches ab exists if and only if this distance can be made as small as we would like by forcing the point x, comma y to be sufficiently close to the point a, comma b in the domain. In other words, if I give you any tolerance, if I say, hey, does this limit exist? And I can take any tolerance, any really small number, and associated with that small number, a distance away from L, I can find an appropriate distance away from our constant point a, comma b, such that as long as x, comma y is within some appropriate distance of ab, then the output f of xy will be within this tolerance of L. For any tolerance, we say this limit exists. If this limit exists, we write the following notation. The limit of f of x, comma y as point xy approaches point ab is equal to L. And you could also write this as the limit as point P approaches P naught of f of xy equals L. I want to kind of pour some liquor out on the curb right now. I'm really sad. This is not a formal, rigorous mathematical definition. If I were to teach you how to prove the theorems that we're about to state, this would not hold water. It makes me so sad I feel like I'm letting you down as students. I'm making a calculated bet. This concept of a limit actually goes deep into a field called real analysis. And to do this well, I would probably need about 4 or 5 hours to really 4 or 5 hours of continuous examples and discussions and, to really get this to a point where you would understand it. And that was just to begin to start the proofs. And so I'm making a calculated bet that in this case, we're going to go through applications without fully deep understanding. If you're interested, you would go on to a real analysis class. Please pour some liquor out on the curb, light a match, and shed a single tear for me because I'm so sad. That being said, it is really important, even though we're not going to go into the precise definition, it is super important to understand what we mean to be sufficiently close, because this is going to give us insight when we talk about the two-path theorem later in this lesson 8. So, whole idea of a limit is that for a multivariable functions, we say that this limit exists, the limit as xy approaches ab of function f of x, we say the limit is equal to L if and only if we can force the output f of xy as close as we want to L by forcing x, comma y to get really close to AB. The word close here is actually very poorly defined. In single variable calculus, we use the measurement of absolute value between x and a to talk about how close something is. One of the major differences between single variable limits and multivariable limits is that our domain in multivariable have at least two inputs. In our case, we're going to focus in the two input case. And we say that the points x comma y and a comma b are close if the distance between those points is bounded above by some small number that forces f to be really, really close to L. So remember, the distance formula comes directly from the Pythagorean theorem, which you've proved. Awesome. And we say that this is the distance formula. And if we graph this here, we would say as long as we're within some delta, some radius around this point, and we take any x inside this disk, if this x comma y, so this is a point x comma y, produces an output that is within epsilon of L, that is really, really close to L, we say that that limit exists no matter where we are in that disk, right? One thing that I want to say is when we talk about distances, when we're trying to get inside that disk, we often do not include the boundary. So all we're doing is including the inside portion, which we'll kind of shade here. And the reason that we don't include the boundary has to do with the fact that this is a strict inequality. There's no less than or equal to there. That gets us to the concept of forcing f of x really, really close to L by forcing x comma y really, really, really close to a comma b. The same path independence that we talked about previously for limits in single variable calculus should hold in multivariable limits. So in other words, we say that the limit as xy approaches ab of the function f of x comma y is equal to L, if and only if, no matter what path we take towards AB, we always confirm that the outputs converge to L. And this is interesting. Remember, in single variable, there were only two directions that we could go. And what I want to show here is in multivariable, there are a ton of different directions that we can go. We could go along a parabolic arch, which we'll see. We could go along a line. We could go along another parabolic arch. The concept here is that no matter what path I take, no matter how I approach AB, all of the output values along my surface should always converge to L as xy converges to AB. If no matter what direction or path I take, that is true, then we say the limit exists. However, if it's not true, if I can find two different paths that produce two different limiting values, then we would say that that limit doesn't exist. We'll get into that in a future video. For now, I want to wave my hands and just drop some theorems on you. I should be flogged with a ruler for giving you theorems that I haven't actually explained where they come from. These theorems are available to you on our course homepage. I actually have a handout called I think multivariable limit theorems and definitions, and you can download that PDF. It's the same that's available in your course textbook. So here, when you're looking at the limit of particular special functions, so if you have a constant function that has a constant output, this would be a plane at height c. We say that the limit as x comma y approaches a comma b of the constant function c is equal to c. So too, if you have a plane that goes along the z equals x line, basically, so it's independent of y. If you allow x comma y to approach a comma b, this is equivalent to a single variable limit because there's no y in the function. Of course, the limiting value here would just be a. And then here I already see a typo. Sugar. If I have a different linear function where my multivariable function is just the second variable, so f of x y equals y, and I take the limit as x comma y approaches a comma b, of course, there's no x in the equation for this function, so really we're just focusing on y, and this output would be b. So what we just said was that the limit of a constant function is the constant, the limit of the function x is a, and the limit of the function y is b. I'm going to drop another major set of limit theorems on you. So you probably recognize these from your previous life. This is the algebra of limits applied to multivariable functions. So if you have some constants a, b, and c that are in the domain of a function, and then you know for sure that the two separate limits exist. If you have two functions, f of xy and g of xy, and the limit as xy approaches a, b of f of xy is equal to L, the limit as x of y approaches a, b of g of xy is equal to m, then as long as you conclude this to be true, we can make the following conclusions. The limit of a sum of these functions as xy approaches ab is equal to the sum of the limit of these functions. So if the individual functions have limits and you sum them up, then you can take the limit of each function outside the sum and then just sum the limiting values. The same thing is true for the difference law. The limit of a difference of two functions is equal to the difference of the limit, provided that both of the limits exist. We know for the constant multiple rule, if I take a constant multiple times a function and then look at the limit of that new function, as long as the limit of f as xy approaches ab exists, then I can factor out the constant multiple. The product rule of limits says if I take a product of two functions and then take a limit as xy approaches ab, as long as the individual limits exist, the limit of a product is equal to the product of the limits. Quotient law is basically the same thing. The limit of a quotient is equal to the quotient of the limits. The one condition that we have is that the limit of the denominator is non-zero. And then this is where we get into the assumption that m and n are integers. So you can think about this as like positive 1, positive 2, positive 3, 0, negative 1, negative 2, negative 3, etc., etc. If I take the limit of a function raised to a power, that's equal to the limit of that function raised to a power. So I can bring powers outside limits. And the same thing is true for rational powers. There is kind of an interesting thing about basically evaluability. If you have 1/2 right here, you got to make sure that the thing inside is non-negative because 1/2 is a square root. Those are some kind of formal conditions. But the point is, the same rules that you know and love from Math 1A are basically still applicable in Math 1C, just done from a multivariable perspective. We're going to do one quick example in the next video just to demonstrate that things are kind of cool. And then we're going to do some other examples in future videos to demonstrate that things are way cool. That this is not just old boring stuff that we've seen before, that there's actually a lot of subtlety going on in multivariable limits. For now, I'll see you in the next video.